Welcome back. All right, what we're going to do is I'm going to go through a description of the internal forces and finding a few before I start in on the shear and moment diagrams. So let's do problem 7.7. It says determine the internal normal force, shear force, and moments at points C and D, right here and right there, of the hang on, of the simply supported beam. Point D, this is important, is located just to the left of the 2,500 pound load. Now, before we can do anything, I have to know the load here. I have to know the load right here. And pretty much everything. Now, let's be completely legitimate here, and let's just say there's an AX, an AY, and a BY. There's a reason there's no BX, and that is because this is allowed to roll back and forth on this little ball right there. So in fact, there is no X force placed there. So the first thing we're going to do is we're going to sum the forces in the X direction equal to 0. There is no X force from this, nor that. So there's no applied X force at all. So in fact, all we get is that AX equals 0. So this term doesn't even exist, so to speak. Now, we need to find this load and this load. So there are two ways to progress here. One is to sum the moment about B, thereby determining A, Y. And then the second is summing the moment about A, thereby determining BY. The other is to do one of them and then sum the forces in the Y. So let's progress both ways. So let's sum the moments about A, and we'll just make this to be positive. If you're going over here to A, we'll start with this 500. Essentially, it's the same thing as putting a load straight down right here, right in the middle of that distribution, equaling to 500 times, we got 3 foot, and 3 foot gives us 6 foot. And it's put right there about 3 foot over from the left. So what we'll have is, now, since we're summing moments about A, this thing basically goes like that. So it, in fact, goes minus 500, 6. And what's the moment arm here? The moment arm is 3. So there's our moment arm. Took care of this one. Now let's take care of this one. Well, this one's going down. So is this one. So it's minus as well. 2,500. Quite a big load. And it's all the way over 9 foot. So the only other thing I have left is BY itself. BY, of course, is going the opposite direction, meaning it's plus, well, I could do it right here, plus BY, and it's not 3, it's not 6, it's not 9, but it's 12 foot over. Now, you solve for that by dragging this on the left-hand side and dividing by 12, and you get By is equal to 2625 pounds. So that tells you this. Now, first thing you can find out is this is, 3,000 pounds being shoved down right there. So if it's 3,000, let's try the sum of the forces in the y direction equal to 0 would equal to, and let's go ahead and make up positive, which usually is what happens. You get AY plus BY minus 3,000 minus 2,500. And you drag the BY, you drag all this to the other side. What you get AY is equal to 2875. So, there's another way of finding AY as well, and it's something to be considered here, and that is, let's say we sum the moments here. When I change logic, I'll try to change pen color. If I sum the moments about B, I'll go ahead and make this positive. So now I'm summing the moments about this area right here. Well, first thing I notice is AY is rotating in the obvious or opposite direction as the positive. So it's AY times again that 12, and just go down through the forces. Okay, so positive 3,000, this load right here, it is now this distance, or 9 foot from that end. And then this load right here, which is 2,500, and it's only 3 foot from that end. So that tells you AY, move this term to the left-hand side, it just becomes, not too surprising, 2875. Same number you got there, you should get the same number. If you don't, something happened. So we've actually determined those loads. Now what do? We need to use those in order to determine the loads at the points that we're interested in. He's identified these 2 points, and so what I'm going to do is I'm going to kind of clean up the diagram a little bit, and we're going to basically focus on point C here first. So how should we do this? Well, you got 2 ways. You can chop the beam, and point C is right here, and you can look at the left end, which looks like this. Or you could chop the beam and look at the right end. The right end looks like this. So whatever you're doing, you're chopping the beam. And the answer from looking at this end should be the same as looking at that end. So let's look at the internal loads. Kind of depends on which one you want to do. Doesn't really matter. However, I do notice that there are fewer loads if I look at the left end. So let's do the left end. And I'm going to redraw it to make it look nicer, since now I know what I'm doing and why. What you see is a beam with a distributed load here. You see AY, which is equal to 2875. You see this 500 pounds per running foot here. But guess what? C is right here, and this is only 3 foot. Now, the loads on the right side, And I'm going to draw the vector in a particular direction. We'll say we're going to draw this one down. I believe that's probably the direction it's going to be. We'll put the shear at point C. We'll go ahead and put a moment at C, and then, I don't know, a normal at point C. All right. Here you're doing something very similar to what you're doing otherwise, or what you did previously. It's just instead of working on the entire beam up here, now you're working on a portion of the beam. So let's work on that. Okay, well, let's first sum the forces in the x direction equal to 0 equals to, and I have, here I'll make that positive, I'll have the normal at point C equaling to 0. There's no other x load. So there isn't a normal at C. The little wheel over here on this end essentially allows it to move around if it's expanding any or not. So it's just straightforward. Now I can sum the forces in the y direction and just make this positive. Doesn't matter which way I make positive, but what I have is 2875 from this load. Then I have the load that gets replaced right here, minus 500 pounds per running foot times 3 running feet. Then I have a minus, because this is going in the same direction, going down here, VC. This thing amounts to 1,500. So I get a VC of 1,375 pounds. So I've determined this one and I've determined that one. Now the only way to find the moment is you have to use a moment equation. So I'm going to sum the moments, and I'm just going to go ahead and sum it about C. Might as well. I'll go ahead and make that positive. That's equal to 0. Now, this load is going like this around C. So it's a minus 2875, and its moment arm is 3 foot. 3 foot right here. Then I got this load right here coming down, going in the positive direction around C. 500 pounds per foot, 300 running feet. 3 running feet, sorry, not 300. 3 running feet. Moment arm, 1.5 feet. That's the moment produced by that. Only thing I have left is the moment itself. Has to go in here. So, oops, what happened here? So, turns out that this and this go in the same direction. So, what I end up with is an internal moment equaling to 6375, and it's positive, so it's foot pounds or pound feet, doesn't really matter. So in fact we figured each one of these out. So the answer to the first one, 0. Answer to the second one, 1375 pounds. Answer to the moment that these are the internal loads in that beam at point C. Now that I've solved this, I'm going to move it down because he wants me to solve it again for a point located just to the left of that load. That's very important to know where that load is, to know where that point is, I'm sorry. So here, let me grab this, get it out of the way. Uh-oh. We'll come down, sort of move this down on the page, and hopefully I'll do okay. Uh-oh. Gonna have to pause the video now. Oops, came back. Well, interesting. Don't know what happened. Too scared to find out. So what I'll do is I'll copy this picture down. Okay, sorry about that. The picture is a little smaller. But I'm wanting to know the load just to the left of D. Now wait a minute, was it to the left or right? Okay, just to the left of the 2,500 pound load. So we could split the beam into two parts. One part here. I'll even do it on this. Okay. All right. We have split the beam. I have the beam split in two. And you notice I put the vector on this part. So this is like the 2,500 pound load over here. But on this side, you don't see that. So, and sorry, I clipped the top of the 500 as well. So what you have is a normal. You also have a shear. And you have a moment. And here I've made a mistake. That is the shear at D. Well, interesting, because you could do it like this. Let's see, you could do this, and you could do this. Now, if I look at this one, I have a whole lot more loads here. I've got that right load, I'm sorry, left load, or the A, Y. I have BY, and I have this one. So, but it seems to me that it might be easier to calculate this whole thing off of this diagram than off of this one, because one, I have to take care of that distributed load, and I think I'm going to opt for doing things as simple as I can. So here, so I'm going to work off of the right diagram. Well, okay, so what happens here? Well, some of the forces in the x direction tend to tell you that, oh, that's a D as well, that the normal force at D is just equal to 0. Doesn't have one. Some of the forces in the y, okay, some of the forces in the y, I should have put a sign direction here, but I'll put a sign direction here. Get BY. Well, what was BY? I'm going to have to look back up the page. BY is 2625. So that's your BY. Oh, and you got 2,500. And you got V shear at D. Well, I think that's 125 if I'm not mistaken, plus D. So in fact, I get the shear at D equaling to minus 125. What the minus means is simply flip the vector over and have it point down, and it's 125. But we're just going to leave it as a minus and not worry about it. Now, sum the moments about this D location, and I'll just make this positive. All you get, now here's the key, this load produces no moment about D, even though it's a large load, because it's technically right over the top of D. Or if it's just to the D is just to the left of that load, it's like 2500 times a moment arm of, say, this small, because it's just slightly to the left of it. And by the way, if I don't have enough zeros in there, I can just put a few more zeros, and that's still greater than 0, and it's still to the left of it. So in fact, the moment arm is essentially 0, although it's not exactly 0, and the moment produced by that load is 0 as well. So the only moment you get is due to this load, which we checked before, and it was 2625. The moment arm there, 3 foot. Is it positive? Yeah, because if it went around that, that's the same direction as this. Now, what do I have this? I have this MD drawn in the opposite direction. Well, so that means the moment at that point D is equal to 7875 foot-pounds. Okay, now we know we have our trusty dusty all-purpose software. Let's check this out. We want to see. Let me see if I can bring the website up, find it, whatever. Okay, I have it in the other window. I'm about to drag it across into your view. Here it comes. A little bit too small, so I'm going to make it a little bit bigger. And now I'm looking, I know the problem was work behind it, but I'm looking over here at the picture to figure out how to make the beam. Okay, first of all, this is in feet. So I'm going to put it in feet. Force units look like they're all in pounds. So I'm going to make a beam. And that beam, turns out it was 12 foot long. Add it. So there's your 12-foot beam. We'll add a support. On the left, it was a pin support. It was located at 0. Then add another support. That was all the way on the right. It was kind of a roller support. It was at 12. Then I got a distributed load. So add a distributed load. The starting location was 0. The ending location was 6. It was 500 pounds per foot on the left and 500 pounds per foot on the right. There it is. Nicely done. Then I'll add a point load, and it's straight down. It's located at 369 feet. It is 2,500 pounds. So there you go. And I like this. It scaled it so that this forced that distributed load to get smaller. So, shall we solve it? I think so. And then it goes through, you'll see the little thing going through the circle up here. Okay. Interesting. So, first of all, where was our point C? Was at 3 feet. So you run down here to 3 feet. And you know, I tried this before, and it didn't do anything. Shear force diagram. The shear force at 3 feet along the beam. And it says no location entered. Let me hit the enter. So in fact, you can't I mean, I can enter that, but it keeps saying no location entered. Can't really do that. So I got to sort of guess. What I can do is I can put a straight line in here and figure out where it is and its value. But of course, let's take a look and make sure. Okay, there's the 2875. That's actually what I've got for the load. So 2875 right here. And there's the 2625 over here. So your key is be able to draw right down the middle and get the value halfway in on the shear diagram. Let's see, what did we get for a shear there? 1375. That's about right, I would guess, if I had to look at this thing. However, I could actually find it by looking at the rise over the run. Here's how I would do it. So this line is actually shear is equal to AX plus B, slope and intercept. Well, the slope is the intercept is 2875. Slope is a minus value times, in this case, x. So I've just got the equation of this line. All I need to know is find out what the two ends are. And that's all I need. What you see, and unfortunately that's going to have to disappear to do this. There is a value there, and there's a value there. You could go ahead and pick that one. 5.75 and 0. That's X and Y. So here. Well, this is beside the point. But in any case, I don't want to get too far off on this. But you're running about 3 meters. That's about where you're at. Let's look at the other point. And the other point is just to the left of that load. Oh, let's look at the moment back there. The moment we got was 63.75. So look at the moment diagram down here. Look at this thing. This thing's quite interesting. So you go up maybe somewhere around here. That's about 7,000. So this is about half 7,000. So I could buy into that being the load right there. Tops out, basically declines and then goes straight down. In a later video, or maybe in this one, we'll go in and solve these. Maybe what I'll do is do that in the next video to be posted, so that it'll be all by itself. So let me go ahead and end this, and then I will approach that video as, let's put the shear and bending moment. So I'm going to call this to a close, and we're going to come back to this very same problem, and we're going to determine the loads there, shear and moment, as a function of x.